discuss about the logic micro operations, right? In previous videos, we are discussing about the arithmetic micro operations. Now we would like to discuss about the logic micro operation. We know that the micro operation is an elementary operation which is performed on the data stored within the registers. Let us consider an example, that is the register R1 and this is the register R2. The content of the register R1 is, let us consider 101. We know that the data within the registers are stored within the binary form and the content of the register R2 is 110. So the micro operation is an elementary operation which is performed on the data stored within the registers. For example, I am going to be consider R1 and R2, right? This is the AND symbol. In digital logic, to represent the AND, we are using this symbol. To represent OR, we are using this symbol. To represent NOT, we are write bar, right, above the any letter. And to represent the exclusive OR, we are going to be use these symbols in especially in logical micro operations. So the logical, especially the logical micro operations, perform the operations in bitwise manner. For example, let us consider A value is 1101 and B value is right 1011. Let us consider like that. Now I would like to perform an exclusive OR operation, A exclusive OR of B. We know that A exclusive OR of B means A B bar plus A bar B. Now I am going to be perform this one in bitwise. Suppose A equal to 1101 and B equal to 1011. That means this bit is exclusive OR with only this bit only, and one exclusive OR of 1, the output is 0. This bit is exclusive OR with this bit only. 0 exclusive OR of 1, the value is 1, and this bit exclusive OR with this bit only. 1 exclusive OR of 0, the result is 1, and this bit exclusive OR with this bit only. 1 exclusive OR of 1, the result is 0. So hence we understand that the logical micro operations performed on bitwise data stored within the registers. And friends, we remember carefully, there are 16 logic micro operations. I am representing this one in a ordered manner. Please remember carefully. The first logic micro operation is represented as F0. F0 equal to 0. This means clear. F1 equal to X. F2 equal to Y. Because to perform logic micro operations, there is a need of at least one operand, and some operations there is need of two operands, two bits like A and B. And F3 equal to, I am going to be consider X bar, that is not, and F4 I am going to consider Y bar, and F5 I am going to be consider X or Y, right, and F6 I am going to write X bar or Y, and I am going to write here F7 equal to X or Y bar, and F8 equal to X or Y whole bar, and F9 equal to X and Y, and F10 equal to X bar and Y, F11 equal to X and Y bar, F12 equal to X and Y whole bar, right? F13 equal to x exclusive or of y, and f14 equal to x exclusive or of y whole bar, f15 equal to all ones. So these are the 16 logical micro operations. It is possible we are going to be draw a truth table for these logical micro operations. How I am going to be draw the truth table for these all operations? Please observe carefully. I am going to be consider two operands x and y. There are the 16 outputs f0, f1, f2, f3, f4, f5, f6, f7, f8, f9, f10, f11, f12, f13, f14, and f15. 16 outputs. Now I am going to be consider the x and y values are 0. I am say that simply remember keep first 8 zeros, 0, 0, 0, 0, 0, 0, 0, and 0. That is, these are 8 zeros. After that, 8 ones, 1, 2, 3, 4, 5, 6, 7, 8. Right? Suppose the x and y operands values are 0, 0. This is the output of the 16 logical micro operation. 0, 1. We keep four zeros, 0, 0, 0, 0, four zeros, again four ones, 1, 2, 3, 4, again four zeros, 1, 2, 3, 4, and again four ones, 1, 2, 3, 4. Right? Suppose the x and y operands values are 1, 0, we keep only two zeros, 0, 0, and two ones, and again 0, 0, and two ones, again 2 0, 0, 0, and two ones, and again 0, 0, and two ones. Suppose the x and y operations are 1, 1 values, we keep 0, 1 alter 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and 0, 1. We know that F16 is all ones. It is suitable. You can understand easily how you are going to be draw the truth table. But to implement the logical circuit, now we are going to be design a logical circuit. Design of logic circuit. To design the logic circuit, I am going to be use one 4 by 1 multiplexer, right, and one logical AND gate and one logical OR gate and one logical exclusive OR gate, and one logical NOT gate. We know that the output of these four gates, again I am going to be explain, the AND gate is a one of the basic logic component. This is like that. It has the two inputs x and y. The output is x and y. Right? We are going to be, this is the output of the logical AND gate, and the output of the logical OR gate is like that. The function, that is, again we are going to be consider two inputs x and y. The output of the logical OR gate is x or y. We already know that several times. This is an exclusive OR gate. It has the two inputs, that is x and y. Then the output is x exclusive OR of y, and NOT gate has only one input, right? Like that, we are going to be given x. This is the x bar. By using these four logical gates, I am going to be draw the actually logical circuit. Please wait how I am going to be draw. I show to you here. I am going to be draw the logic circuit. The first of all, I am going to be consider one 4 by 1 multiplexer. So I am going to be consider a very lengthy 4 by 1, a very big 4 by 1 multiplexer. We know that 4 by 1 multiplexer is a combinational circuit. It has the four inputs. This is the zero input, this is the first input, this is the second input, and this is the third input. It has the two selection lines, that is the S0 and S1. Right? For the first input, I am going to be connect the output of the AND gate. For the second input, I am connecting the output of the OR gate. For the third input, I am connecting the output of the exclusive OR gate. For the fourth input, I am going to connecting the output of the NOT gate. For these gates, I am going to be given the inputs like that. Now, this is the input of A. I am going to be consider or A, and the A is connected to the all the gates, input to the all the gates, and A only connected to the NOT gate, because we know that the NOT gate has only a single input, and this is the input B. The input B is connected to the second input B is connected to the all the gates in like that. Now this is the output of the entire circuit considered as D. The output D value is depending upon the S selection lines S0 and S1 values. Now let us consider this is the S1 and this is the S0. The S1 and S0 values are 0, 0. The output D, we know that the first input of the multiplexer, which is the output of the AND gate, that is transferred to the output D. That is here A and B is performed. Suppose the S1 value is 0 and S0 value is 1, then the second input of the multiplexer, which is here, which is connected, the OR gate is connected. The output of the OR gate is turned as the output of the multiplexer, A or B. Suppose let us consider the selection lines is 1, 0. That is, we know that the third input or of the multiplexer, that is which is connected to the exclusive OR gate, is turned as the output, that is A exclusive OR of B. The finally, right, let us consider 1, 1, S1 value 1 and S0 value 1. That is, what is the fourth input of the multiplexer? Only consider connected A. This is connected A. Please observe above A. That is the finally we are going to be getting the A bar. These are the four basic logical operations. Right? This is the design of the logic circuit. Okay, friends. I hope you can understand this one. Thank you.